Let us see this problem. We are given a text and a pattern. We need to find if pattern is present in the text or any of its permutations is present in the text. So when we say permutation, two strings which are permutations of each other are also called anagram. So we need to check if pattern is present or an anagram of this pattern is present in the text. Let's understand the problem with these examples. Say our text is geese for geese and our pattern is frog. So if you look for frog and its permutations in the given text, you will find that FORG and FROG, they are permutations of each other. So our output is yes, it's present, its permutation is present. Now let's see this example. We have this text and we have this pattern. Do we have permutation of this pattern in the text? See, we have these characters E, E, K, S. We also have these characters here, and we also have R, but they're not contiguous. We have a G in between, right? So the answer is no. We do not have a permutation of the string present in the given string at contiguous locations, right? So there should be a substring which should be anagram of the given string. We can't take the non-contiguous characters. Now please pause this video and try to write a program that takes a pattern as an argument, a text as an argument. It returns true if the pattern is present or any of its permutations is present. Otherwise, it returns false. Let us first talk about the naive solution to solve the problem. Here we have C++ implementation and this side we have Java implementation. Let's say we have this text and this pattern. What we do here is we slide this pattern over this text one by one. We first bring frog here and then check if they are anagram. Then we slide the pattern here and then check if they are anagram. Then we slide here and then check if they are anagram. That's the simple idea. And this code is just anagram checking code, right? You can ignore this code. We have already discussed anagram checking in an earlier video, so you can ignore these functions are anagram. They're simply checking if the two things are anagram of each other or not. It checks if pattern and text beginning from I, they are anagram of each other or not. If they're anagram, it returns true, otherwise it returns false. Now if you take a look at these main functions, they are very similar to naive pattern searching. We are finding the length of the text, then we are finding the length of the pattern, and then we are sliding the pattern over the text one by one. We begin with I equal to 0 window in the text, right? And we go till n minus m. So here your pattern length is 4 and text length is 13. So till which index you are going to go? You are going to go till this index, and this index is 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This index is 9. Till this index you will go. So you go through every index and then you check if the text at the current window and pattern, they are anagram of each other or not. If they are anagram, you immediately return true. And if you never found an anagram, then you return false. Now let's talk about time complexity of this solution. This solution clearly requires big O of n minus m plus 1, right? These many times this loop will run in the worst case into m, where m is the length of the pattern. This is the time required by the solution. I am assuming that alphabet size is constant, so I am not counting this char in part of my computations. Char is 256 here. In C++ you can define a char, and similarly in Java you can define a static final variable with value 256. So I am not considering char. This is the time complexity we get, and if we do not consider char, we can say auxiliary space is also big O of 1. Now please pause this video and try to think of an approach that takes linear time, works in linear time to find if an anagram of a string is present in a pattern or not. Let us now talk about an efficient solution to solve the problem. This efficient solution is similar to the naive solution. It's basically an optimization over the naive solution. The idea is same. We are going to slide this pattern over the text one by one, and then we are going to compare if they are anagram. The current window of the text matches with the pattern or not. So how do we do this? Here in the earlier solution, naive solution, what we were doing, we were sliding and then we were calling R anagram function for every slide. And R anagram function was computing the frequencies of every character in the pattern and computing the frequencies of all the characters in the current window of the text. And if these frequencies were same, then it was returning true, otherwise it was returning false. So the optimization that we do here is at the R anagram function. We don't call this function anymore. what we do here is we slide the pattern like the naive solution over the text one by one. So first we have the pattern here, and we have initially computed counts of characters in the first window of text and the pattern, right? So this is what we do in the first loop. We have a frequency count array for text, count in text CT, count in pattern CP. We have initialized both these arrays as 0. So char is a constant here, which is 256, right? In Java, you can say char is a static final variable, which is 256. In Java, both CT and CP arrays are initialized as 0, 0. So we have first initialized the count arrays. Now we have computed the counts of characters in the first window of text, which are these 4 characters, and full pattern, these 4 characters of the pattern, right? 4 characters of the text. And this is initial count that we have for text, and this is initial count array that we have for pattern. For G we have 1 occurrence, for E we have 2 occurrences, for K we have 1 occurrence. For F 1, G 1, O 1 and R 1. So this is similar to naive method that you first compute the frequency and then you check whether they match or not. Now the different thing that we do here is the optimization that we do here is over the naive method. When we slide the window to the next window, right? When we move from this window, previous window was this one, first window, and our next window is this one. When we slide the window, we just have to remove this character and add this character. And for that, we can simply go to the count array and reduce the count of G by 1, 0 and add the count of S. So we add the count of S here, 1, right? That's all we need to do. And this is big O of 1 operation. And that's the trick here. Sliding window trick. When you slide the window in the text from previous position to next position, you just need to remove the first character of previous window and you need to add the last character of the current window. So we added S and removed G when we came from here to here, right? Now when we move to the next window, our next window is this one, right? And our previous window is this one. What all we need to do is we need to reduce the count of E by 1 and we need to add the count of F by 1, right? So E's count becomes 1 now and F's count become 1, right? So F would come here and its count is 1 now. So that's our new frequency array. We compare these two frequency arrays again and then we check if they're same or not. Let's now take a look at the implementation. In the implementation here, first thing is we compute the count for both the arrays, right? Both the first window of text and pattern, right? After we have computed the initial counts, we are sliding the window one by one. And before sliding the window, we are checking if the current counts are same. Here is the function rsame. I have not written implementation of this function. This function simply checks whether the contents of these two arrays, CT and PT, they are same or not. This is as simple as that. If CT and PT have the same values, then it's going to return true, otherwise it's going to return false. So we check the current counts. If the current counts are same, then we return true. Otherwise, we remove the previous window's first character. This is where we remove the previous window's first character. How do we find out? I is the index of last character of the current window. We go to the previous window's first character using I minus pattern length. We go to that index, right, in the text, get that character and reduce the count of that character by 1. Same as in Java. We have caret function in Java instead of square brackets. We go to that index, that character at that index, and we reduce its count by 1. And we are adding the last character of the current window, text.caret I plus plus. So we add the last character, remove the previous character, remove the first character of the previous window. And at any point, if we find CT and PT are same, we return true. Let us now talk about time complexity of this implementation. So we run this loop which runs for pattern length time. We are doing constant work inside it. So it's big O of M work if M is the length of the pattern. So this is big O of M work, or we can say theta of M work. It's always going to take M time. Now inside this second loop, we run it n minus m times because we begin from pattern length and go to the text length. Here m is the pattern length and n is the text length. So this loop runs n minus m times. Right? Inside this loop, we are checking if these two character and if these two arrays CT and PT are same or not. If these two arrays are same, then we return true. So this work is going to take theta of char time, right? Because you have char sized array and you're checking if these two arrays are same or not. So if we want to be precise, we can say time complexity is theta of m work in the first loop plus n minus m into char. That's the, or we can say big O, because you may return somewhere in between into char. That's much work we are doing in this function. So I've simplified this time complexity because I can say this is m into char upper bounded by m into char, and then we can say n into char because m is smaller than n, right? So I can say it's n into char. That's the simple form of the time complexity. Auxiliary space it requires is big O, theta of char, because there are char character, two arrays of size char characters. Now if we consider char as a constant, consider all the ASCII values or only lowercase alphabets or uppercase alphabets, then you can say its time complexity is linear and auxiliary space is big O of 1 or theta 1.